I will present a problem on analysis of partial differential equations. I really find this problem interesting for me. You have a function on two variables, x and y, which is e to the minus x times sine y. And x and y belong to the two-dimensional Euclidean space. First question is to prove that U is harmonic in R2. The second question, you have to compute explicitly the L2 norm of the U and its variation, where omega is a bounded region in the Euclidean space. This region omega is a bounded region in the two-dimensional Euclidean space. And finally, the third question, you have to show that the H1 Sobolev norm of the function is equal to a constant times the L2 norm of the variation of the function. This constant is square root of 6 divided by 2. Let's start with the first one. We have to show that U is a harmonic function. So we take the Laplacian operator on the function U, Laplacian of e minus x sine y. And basically I have to find what is the second derivative with respect to x of that function, plus the second derivative with respect of y of that function. I take the partial derivative with respect to x, so I don't see this function sine y will go outside of the partial derivative. And now here I take the partial derivative with respect to y, so the e to the minus x will go outside of the partial derivative. Okay, I take the second order partial derivative of the exponentially decaying function. If I take the partial derivative once, I'm gonna get minus e to the minus x. I take again the derivative of that function, I get e to the minus x plus e to the minus x. I take the partial derivative of sine of this trigonometric function with respect to y, I get cos y. And then I differentiate the function, the cos y, I get minus sine of y. Okay, let's take common factor sine y. And inside the brackets we have e minus x minus e minus x. And of course this is equal to 0. Sine y times 0, and altogether I get that the Laplacian of u is equal to 0, and this leads that u is harmonic function. For every x and y in the two-dimensional Euclidean space. Number 2, I want to calculate the function u, the norm of the function u, the L2 norm, in the bounded region omega, and take the square of it. So that's the integral over the region omega. Omega is a bounded region in R2 of u squared d omega. So I have 0 pi, e to the minus x sine y raised to the power of 2 dx dy. That's e to the minus 2x sine squared of y dx dy. I can interchange, so basically here I have a double integral. I can start from the integral inside, so I have 0 pi e to the minus 2x dx, and the integral from 0 pi, the sine square of y can be pulled out like this. So I have the integral from 0 to pi sine squared of y e to the minus 2x over minus 2 0 pi and dy. This is going to be sine square of y e to the minus minus 2 pi minus e to the power of 0, which is 1, over minus 2 dy. Here, this one, it's just a constant. I can pull it outside the integral, and I also polish this term. So it's going to be 1 minus e to the minus 2 pi over 2 times the integral from 0 to pi sine squared of y dy. That's pi here, it looks like r. My pi is not very good. So that's going to be 1 minus e to the minus 2 pi over 2 times the integral from 0 to pi. Sine square of y is going to be 1 minus cos 2y over 2 dy. I use this trigonometric identity. For the integrand of the for the integrand on this integral here, and here I can split the integral from 0 to pi 1 over 2 dy minus 1 over 2 from 0 to pi cos 2y dy. The first integral here is going to be a half times pi minus 1 over 2, and here this integral is sine 2y over 2 0 pi. Minus a quarter, sine 2 pi minus sine of 0. This term will vanish completely, and I will have 1 minus e to the minus 2 pi over 2 times 1 over 2 times pi. And I can work this out further. Is 1 over 4 times pi times 1 minus e to the minus 2 pi. So my L2 norm squared in the bounded domain omega is gonna be 1 over 4 times pi 1 minus e to the minus 2 pi. And I have to calculate the variation of the function, the norm of the variation as well. So it's going to be the integral from 0 to pi, integral 0 pi, grad u squared dx dy. So it's going to be 0 pi, 0 pi. I take the gradient of u, and I take the, so it's going to be e to the minus e to the minus x sine y, e to the minus x cos y, the normal, the absolute value of that squared, dx dy. So I have the integral 0 pi, the double integral. This is e to the minus, so e to the minus 2x sine squared of y plus e to the minus 2x cos squared of y dx dy. The computations will be simplified because I can take common factor e to the minus 2x, and sine squared plus cos squared is 1, so I have e to the minus 2x dx dy. And that is gonna give me e to the minus 2x over to 0 pi, and then the integral from 0 to pi dy, so minus 1 over 2. So it's gonna be, let me change the signs directly here. So the norm of the variation in L2 is a half 1 minus e to the minus 2 pi times pi. That is my final answer. And of course you can see here that I've showed that the u L2 squared is 4, 1 over 4, and this term here multiplied by this term here, and the gradient u L2 squared is a half. So I can write this the norm of the variation as 2 times the norm of u in L2 squared, which is bigger of course than the norm of u in L2 squared. So the norm of the variation of the function is bigger than the norm of u in L2. And then I want to calculate the Sobolev norm u h1 omega squared is gonna be u, the norm of u in L2 squared, plus norm of gradient of u in L2, and this is the norm of u in L2 is what? Is a half of the norm of the variation plus grad u L2 squared. So that's a half plus 1 grad u in L2, and this will give me u h1 equals 3 squared here, 3 over 2 grad u L2 squared, and here the u in h1 is gonna be square root of 3 over square root of 2, the variation of u in L2 without the square here. And if I polish this a little bit, I have the norm of u in h1 equals square root of 3 square root of 2 over 2 grad of u in L2, and that is gonna give me u h1 equals square root of 6 over 2 grad u in L2. And so the h1 norm is a constant times the norm of the variation in L2.